Our first unit this semester is on gases, okay? And I love gases as a unit because it's something that you have familiarity with through balloons. All right. So, as part of our initial discussion here, I would encourage you to maybe pause the video for a sec. And if you have a balloon at home that you could blow up and use kind of as a model for yourself while we're talking, that would be helpful. Otherwise, you can just watch me or you can picture a balloon, but you certainly all probably have plenty of experience with balloons to be able to think about it. And that's something that I would say about AP chemistry. Okay. Um, a lot of times, I think we tend to get in our own way by overcomplicating concepts that we actually already understand. And when you go to take your AP test in the spring, they want you to have a good conceptual understanding of um, chemistry phenomenon, and that includes something as simple as a balloon. Okay, and so um, when you're doing this work and you're thinking about these concepts, try not to um, overcomplicate it and picture a balloon in your head and try to think conceptually like, okay, if I were to do this to the balloon, what would happen? And then how does that translate to specific chemistry vocabulary um, so that I can demonstrate my knowledge? All right. Because a lot of times that's really what you're doing is you're just taking concepts that you're already familiar with and you're translating those ideas into a new set of vocabulary that's relevant to chemistry. Okay. All right. So my balloon right here is one that I blew up myself with my own air from my own lungs. So it really is filled with air. Okay. And as you know, air is a homogeneous mixture. And if you recall from the summer work, which was ages and ages ago now, homogeneous mixtures are mixtures where every part of the mixture is evenly dispersed throughout the mixture itself. And so in our air, for example, we have 70% nitrogen, 21% oxygen, and then a whole bunch of other gases in smaller quantities like CO2, H2O. There's even helium in our air, there's argon, there's carbon monoxide, there are all sorts of things in our air. And the way that I always explain it is we rely on the fact that air is a homogeneous mixture because the part we really need is the oxygen. And that only represents about 21% of the mixture. And we don't spend any time in our daily lives thinking about, oh, where in this room is the good oxygen? Because the answer is the oxygen's everywhere. Because again, air is homogeneous, meaning all the parts of the air have spread out evenly throughout the entire sample. Okay. And so no matter which corner of the room you're sitting in, you have 70% nitrogen and 21% oxygen, and then a whole bunch of other gases. Okay. So just keep in mind that's one of the properties of gases is that they form homogeneous mixtures with each other no matter what. Okay. And that's something to think about. All right. And one of the reasons they do that is because gases, no matter what type of gas they are, whether it's nitrogen, water, carbon dioxide, carbon monoxide, chlorine gas, which is really toxic, whatever type of gas, even if they're very different chemically and have very different properties, gases have a lot of very similar physical behaviors. Okay. And so this unit really looks at what are the similar physical behaviors of gases and how are those behaviors predictable. And so that's what I want you to think about. Okay. So I'm going to encourage you to take a minute right now and play with your balloon or think about a balloon you've played with in the past. I am going to screen share with you from my iPad in just a sec. Okay. But the more you can activate your prior knowledge and your experience with balloons, that would be helpful. Okay. Because you want to think about, like, what do you already know about its behavior? All right. And so now a couple of questions. Like, for example, here's my balloon. What if I press on it really hard? Okay. What happens? Or what if it accidentally floats too close to something hot, like a light bulb or the burner on a stove? Okay. I'm sure that you can predict the outcome of all of these situations. Okay. The question is, how can you explain them using chemistry? All right. And what's happening on the inside of the balloon? So, what I would like you to do now is pause the video in a second and actually take a couple minutes to just write down here on the notes file, what do you think is happening inside the balloon? What do you already know about gases? You start learning about the states of matter in elementary school. You know what solids are, you know what liquids are, you know what gases are. You know how they're different. In fact, you've probably learned their definitions in a very simple way. Okay. So, what do you know about gases? Because that's going to be where we start our conversation. So, pause the video, think for a couple minutes, write down your answers, and then when you're ready, hit play again. Okay. In the meantime, I'm going to scroll on. Hopefully, you paused. All right, so here's my drawing of my balloon. It's not the most amazing drawing ever, but it's good enough. All right, and inside the balloon, if you're wondering what are all those dots, when I asked my husband, how did the balloon look? He's like, well, what are all those dots? And I said, those are my gas particles. Then it made more sense to him. So I want you thinking about what is going on with these gas particles right here. Like, what are they doing? Okay, what do you already know about gases? Do they stay still? Do they move? What do they do? Okay. And you guys probably already know from things you've learned earlier in school that gas particles are constantly in motion. Okay. They have a lot of kinetic energy, which means kinetic energy is energy of motion, in case you haven't taken physics. They have a lot of kinetic energy, which means they're zipping around on the inside of the balloon every which way. And even though to us this looks like a pretty small balloon, you know that this contains like billions upon billions upon billions upon billions of air molecules in here. Okay, so there are, like, if I were to fill as many dots as I could inside the balloon, I wouldn't even come close to representing the number of air molecules that are actually in here, because there's that many. So all of those air molecules are zipping around, okay? And when they zip around, a couple of things happen. First of all, they hit stuff, all right? They hit the sides of the balloon, okay? And they also hit each other. So what do you know about that, all right? What keeps our balloon inflated? Okay, why does our balloon have this nice spherical shape? And the answer is because the air molecules are zipping around so fast in there that at all times there are enough air molecules hitting the sides of our balloon that to us, it just looks like our balloon is keeping a constant shape and nothing exciting is going on. But in reality, it's pretty wild in there, okay? When the gas particles hit each other, they just bounce off, okay? They don't really slow down. They don't stop to say, hey, how are you doing? They don't care, okay? They are moving so quickly. And in general, gas molecules tend to be just that. They tend to be molecules, meaning molecular compounds. And remember, molecular compounds don't have a lot, like they don't have ions or anything. So there isn't a lot of attraction between them. And typically, and we're going to talk about this more, so in case this isn't something you remember from last year, maybe you didn't learn it last year, that's totally fine. But in case you did, there are two types of molecular compounds, polar and nonpolar compounds. And nonpolar compounds are the ones that really don't have even like a very strong positive or negative region at all. Like there's nothing about them that's really attracted to other molecules. And so for the most part, gases are nonpolar molecular compounds. And so they really have very few attractions with other molecules. Okay. So when they're zipping around super fast, they just kind of bounce off each other and just fly in a different direction until they hit something else. And they really just don't care. Okay. So they just kind of go crazy, hit things, move on. They don't get slowed down. They don't get entangled with each other, anything. They don't group up. They just all keep zipping around individually to make to keep the balloon inflated. Okay. All right. So let's talk. The properties that govern the behavior of gases are pressure, temperature, volume, and the amount of gas. Okay. These are things that you probably have experience with and can explain. Like when I'm pushing on the balloon like this, what I'm doing is I'm adding pressure to the balloon. Okay. Temperature, then a balloon changes. Like if you've ever left a balloon maybe outside or in the garage or something overnight, you know how sometimes when people have birthday parties or celebrations, they tie balloons to their mailbox to let people know that's where the celebration is going to take place. Well, what happens to those balloons overnight when the temperature gets colder? Okay, do they look the same as they did during the day when the sun was shining? All right, and the answer is no, they usually don't. I want you to think about how they're different. Volume, that's the space that the balloon takes up, okay? And so I would say to you, like, for example, when I push on this balloon, you can see that it's taking space up very differently than it was when I wasn't pushing on it. Or what happens when I just push in on one point, okay, like that. How does that affect the volume of the balloon? There's a relationship between pressure and temperature. And there's definitely a relationship with the amount of gas and these other things, because like, I don't remember how many times I blew into this balloon. Let's just say 3. If I had blown into the balloon 6 times, it would have been probably twice as big, right? Because I would have been putting more and more air into it. And so the more air you put in, the bigger the volume gets. So again, that there's a relationship between these properties and the way the gas behaves, okay? Because usually what happens is when one of these properties changes, the other properties change as well. The question is how. And here are your 2 choices, okay? And I want you to think about these terms carefully. The first one is directly. So for example, okay, if I put more air into the balloon, okay, so instead of blowing into it 3 times, I blow into it 6 times. If I put more air into the balloon, what happens to the volume? Does the volume get bigger, meaning more air, more volume? Or does the volume get smaller, meaning more air, less volume? If you say the volume of the balloon increases, that means as I increase the amount of air, the volume increases. That's a direct relationship, which means as one goes up, one variable, so does the other variable, okay? On the other hand, inversely means they go in opposite directions. So as one goes up, the other one goes down, okay? And what I want you to do is I want you to think about these variables and your own experience with balloons. And I want you to actually think about and go back to the questions that I asked. Remember, I said, like, what would happen if I pushed on the balloon really, really hard? What would happen if the balloon floats too close to something hot? Okay. What would happen if I breathe more air into the balloon? I want you thinking about all these questions, and I want you, before we move on, to try to figure out what are all the relationships between these variables. In other words, what's the relationship between pressure and temperature? What's the relationship between pressure and volume? What's the relationship between pressure and amount of gas? Because all of these variables are interrelated. And so then you do it again, like, how are temperature and volume related? How are temperature and amount of gas related? How's volume related to amount of gas? So ask yourself, what do you think before you really get going? What do you think are the different relationships between these? Make your predictions. And then in our next video, we'll talk about it more in depth and we'll look at it from a mathematical perspective.